Right, thank you everyone. In the morning I mentioned that I'm going to go really, really fast in the afternoon, but that was just a joke. I think it's a mini course, it doesn't really make sense to accelerate the pace. But it's good to finally see some examples and applications of all these things that we discussed. So I want to start with something in degree 2. All right, or you can think about in the bicritical case, having the sort of the argument are essentially going to be the same. So bicritical means there are only 2 critical points. And I want to present some results by Jen Kiwi and also some results by Homing, Kevin, and Adam Maston. Which relies on all of these techniques and then find some applications in degree 2. So in the morning we defined these rescaling limits, and in degree 2, or in the bicritical case, can we prove that there are at most 2 rescaling limits. All right, and then I also want to talk about how this. There is actually a better, more detailed version of this, which I'll explain in a moment. But then I also want to talk about how this would allow us to prove some boundedness results, which is theorem first proved by Adam Maston using some analytic methods, and then using these Berkovich spaces and these limiting map John trees. Homing and Kevin give an alternative proof. It says that a hyperbolic component of disjoint type is bounded if and only if it's not polynomial. I'll also explain the statement a little bit more. All right, so what's the technique, or what's the idea? Well, the idea here is to understand that.
That's a theorem.
Yes. All right, yeah. So Epstein first proved this term, and Homing and Kevin, they reproved the statement using the techniques that I'm going to discuss. Okay, so and then somehow, so I'm putting all of them in the same bracket. All right. All right. So what's the idea here? Well, the idea here is to look at something called the critical locus and then try to understand the dynamics of the critical locus. So I'm going to define the critical locus as just the convex Hall of the critical ends. So this is going to be a subtree in our Berkovich tree, or in this asymptotic. Right. So these critical ends are those ends associated to the critical points for the sequence. Right. So well, it has some nice properties. So okay, so maybe I'll draw some schematic pictures first, and then I'll explain some of these nice properties. So for example, in degree 2, there are only 2 critical points at the end. So the critical locus here is really this bi-infinite geodesic connecting the 2 ends. Right? So this is both in the degree 2 case or in the bi-critical case. And that is sort of like very important in our understanding about these limiting dynamics, because we can sort of understand the dynamics on these critical locus very well.
How do you know that you have really 2 points and not just 1 point? Maybe the critical locus underneath the right?
Well, I mean, this is because of the scale that we choose. They cannot collide. You can actually see that. Yes, it's part of the argument here. All right, and in higher degrees, this might look, in degree 3, there might be 4 critical points, and then they might, the critical hull might form some more complicated trees. But basically, the principle, the philosophy here is, if we understand the dynamics on these critical locus, then we can say a lot about the dynamics of the tree in general. Right. So some nice properties about these, which I'm going to list, and then I'm not going to write any proof. So first, we can define the local degree. So the degree of a point is the degree of the tangent map. So we have defined the tangent map, which is the reduction under certain normalizations. And the degree of the local degree of a point is simply the degree of the tangent map. And if the local degree is greater or equals to 2, then x has to be in this critical locus. But the converse is not true. Not every point in this critical locus is going to be a local critical point. And these local degrees are constant on each edge of CF, except possibly at the endpoints. And the map is injective on edges of CF. And the map is expanding exactly by the local degree of the map on the edge. So let's say f prime equals to the local degree of the edge D. So this is on an edge. All right, so
are you already using the bicritical assumption here?
none of them. So this is a more general statement. So all of these properties are satisfied for any degree, in any degree. All right, so now we can try to understand the orbit of this critical locus. So let's now we are assuming in degree 2. I'm trying to give you some sense how to prove the first theorem, and then I'll also say something how the first theorem allows us to actually prove the second statement. All right, so now let's look at this critical locus for f. In this case, it's just going to be a bi-infinite line segment, so bi-infinite line, a geodesic. So let's look at its image. Right, so there are really just two possibilities. Either it sort of intersects the critical locus, or it doesn't. Right, so if it does, then there are two possibilities. Either this particular point is fixed. There is this intersection point. Either this particular point is fixed, and in which case you get a totally invariant point. And that is not possible if you are starting with a degenerating sequence. So let's denote this x. I mean, there are more possibilities. These two rays can intersect in a non-trivial line segment or so on. But I'm going to give you one simple example to illustrate some sort of the idea that would allow us to classify the degree 2 case. Okay? So this would be the simplest example when they intersect, and then let's consider x is just the intersection. So from the assumption that we know we do not have any totally invariant point, so x is not fixed, so x must map to something else. So x must be mapped to something, let's say here. All right, and then this line here, this critical locus is mapped to this red one. And if you count the local degree, every point on this red line already has two preimages counted multiplicity. Right? So I should say that this local degree matches with the usual sense of the local degree. Every point has exactly d preimages counted multiplicity. So in this case, everything on this white line would have local degree 2. So it has its image has exactly one preimage, which is this one. Right? So now this means, this forces the image of this, this red one to be something like this. Right? Just by counting degree. At this particular point, you have already occupied everything going along this direction. So this red curve has to go something like this. So this green one is the second iterate of the critical locus. Right? And then you repeat this argument, and then you can see all of these iterate of this critical locus is just not going to be recurrent. So in this case, the critical locus is not recurrent. And this implies that no rescaling limit. Okay? As we discussed previously, if we have a rescaling limit, then we must have a periodic point with local degree greater or equals to 2. And in this case, all the points with local degree 2 are marching off to infinity, and then we do not have any rescaling periodic points. Right? So sort of like this is the first example, and then the proof can be boiled down to studying these kind of different phenomena of how the critical locus and they interact with its image, and so on. Right, so let me just tell you the second possibility, and then try to explain like where you can get this rescaling limit. All right, so let's assume then this is the critical of f. and then its image do not intersect this critical locus. So we can draw this geodesic in between these two lines. Because this is a tree, there is a unique line segment connecting them. And what happens here is that you might have a fixed point in the middle, and then this the whole picture sort of like rotating with respect to each other. So this is originally a critical point, and it's mapped to somewhere here. And then keep rotating. Under some iterate, it might map back to itself. Right? And then there is a little bit of work you need to do. So there are really two possibilities. Either you get a rescaling limit on the nose, or as we discussed previously, this is only a periodic cycle, not necessarily a rescaling limit. And then you have to blow up this point into a smaller scale. And then you can argue in that way that this is not going to be a rescaling limit if it is not, if you do have a secondary scale. Right? So this gives you the first rescaling limit. And now what happens for the second one? What happens for the second one is the following. So you might have some other point on this critical locus. And remember, from the property, the map is going to be expanding with degree 2 along this line segment. So after first it comes back, so this line segment is going to map to twice as long as this this segment. If this distance is L, then this distance is going to be 2L, and then it follows as a isometry, so this is going to be 2L. And then when it comes back to here, it might happen that this whole thing sort of folded along this arc and then covers. So this particular arc may go something like this. And then you obtain a secondary rescaling limit in this way. Right? All right, and then if you do this thing carefully, and then you can prove that this is the only possibilities to get the second rescaling limit, and then this is exactly what Kiwi did in his classification. And a more precise statement is the following. So we're looking at degree 2 rational maps, and we assume that its conjugacy clause goes to infinity. Then there are at most 2 rescaling limits. In the first case, one of the rescaling limits must be a parabolic rational map. So there exists Mn such and Q such that this Mn composed and inverse composed with Fn composed with Mn would converge to something G, which is in P11. So this is a short notation, means that G is in quadratic rational map, and G has a parabolic fixed point. Oh yeah, thanks. All right, so this is the first condition, first situation where you can have one rescaling limit, and this rescaling limit must be parabolic, must have a parabolic fixed point. And the second case is you have two rescaling limit, and in addition to this parabolic rescaling limit, you have another one, and then the second case is even more special. So you have this parabolic rescaling limit. In addition to that, this G has a critical point eventually mapped to the parabolic point This is the first rescaling limit, and then the second rescaling limit, let me denote it by h. And the second one, h, is a polynomial. All right, you can sort of see that in this picture. This direction will correspond to the critical point of the first rescaling limit. And in order to have the second one, this critical point has to map somewhere here. And then this direction is going to map to this direction. And this corresponds to the parabolic fixed point direction.
Are you willing to describe that picture from the beginning? The first rescaling limit, the critical locus goes to the...
All right, so this is the critical locus, and it maps to the red one. All right, and then it might happen that certain iterate of this critical locus, this is going to be a fixed point. And it might happen that this fixed point is a rational rotation, for example. And under certain iteration, this particular point comes back to itself. So you have a periodic point. Right? Now, you might think, well, all the other points are expanding. Right? So you don't expect to have the secondary scaling limit. But there's something special can happen if there can sometimes be another point on this critical locus, which is expanding by a factor of 2. But when it comes back, it maps to somewhere here. And now this white point is mapped to this circle here. And somehow this whole thing got mapped to this purple one. So if you assume that the length between these two critical points, between these 2 points are 2, then what happens is that L plus 2 equals to 2L has a solution, basically. Right? So L, you can choose your point to be something like with the distance 1. No, I suppose. Well, 2. And then this will solve the equation, and then you can find a secondary. And then once you have that, you do not have any rooms for the folding mechanisms to destroy this expansion factor along the critical locus. And that's it. And that's the only place you can get a secondary rescaling limit. Yes?
Here do you mean independent rescaling limit?
Yes, I have not defined that, but what I really mean is independent rescaling limit. Yes. Thanks. Yes.
Can you put this by constructing a holomorphic family having the same rescaling limit, so we can prove it directly by using row construction?
Yes. Yeah, you can do this same construction using this sequence construction directly. All right. All right, and now let me try to explain how this classification is important and to deduce the boundedness problem, boundedness theorem. All right, so maybe I should first discuss what do I mean by a disjoint type, and then what do I mean by a polynomial, and then at least one direction of the proof. So a hyperbolic component is disjoint type. If let's say, f in H, the PCF, or maybe any map, any map f in H has 2D minus 2 attracting cycles. So it has the maximum number of attracting cycles. So in degree 2, this means that you have exactly 2 attracting cycles. And one possibility is that you can just take any hyperbolic quadratic polynomial. So f is a quadratic polynomial, a hyperbolic one. Then it always has this super attracting fixed point at infinity. And since it's hyperbolic, it has another attracting cycle, bounded attracting cycle. So it is a disjoint type hyperbolic component. All right, and then it is easy to see sort of such hyperbolic components are not bounded. So they are bounded in the space of quadratic polynomials, but they are unbounded in the space of rational maps. And then this is closely related to Tyler's submutability theorems in dimension 2, for degree 2. And basically, if you have any hyperbolic component, and they correspond to something in this Mandelbrot set, and each hyperbolic component other than the main cardioid belongs to some ling, and if you make your multipliers at infinity to go to the rotation number associated to the conjugate ling, then you get a degenerating sequence. Right? So it's easy to see that one direction for one direction. Right? And then to prove the second direction, it really relies on this classification and the following observation. So if there exists some p greater or equals to 2 and a p cycle Cn such that when you take its multiplier, is bounded, then Fn has a rescaling limit and this Cn converges to a actual periodic cycle of the rescaling limit. Sorry?
You still assume that the sequence degenerates?
I'm still assuming the sequence degenerates. Well, yeah. Let's assume that. It's an argument by contradiction, and then let's assume that. But you can also, well, maybe if you allow your period to be of your rescaling to be 1, then I think this is also true in general. Of let's say G. Well, so what do I mean by an actual periodic cycle? Well, so here the rescaling limit is defined by the convergence of the coefficients. But what's nice about this this convergence is that you can also think about this as the convergence compactly away from finitely many points. Right? So there are finitely many points where you have some cancellation of the poles and zeros, and away from those points, the convergence is compact, is uniform on compact set. Right? And then here, like these actual periodic cycles, what I mean here is just those periodic cycles of this rescaling limit G that is away from these holes. All right, and then now the argument follows directly from Fatou Shishikura's inequality, or maybe simpler, since not only do we know if we have a hyperbolic component of disjoint type, which is not polynomial, that means we have two different periodic cycles where each of the periods is greater or equals to 2, and the multipliers do not go to infinity. And then, in fact, the multiplier is actually bounded by 1. The modulus of the multiplier is actually bounded by 1. So by the Fatou Shishikura's inequalities, they must, and then you first use one of the limiting cycles to construct the first rescaling limit, G. And we know G is parabolic, so this parabolic fixed point already attracts some critical points. But now we have another non-repelling periodic point, and this point must attract another critical point. Right? So we cannot have the second rescaling limit because in the case 2, in order to have a second rescaling limit, the other critical point has to be eventually mapped to the parabolic fixed point. Right? And then that's the contradiction. So we cannot have two cycles, both of period greater or equals to 2, converging to some non-repelling periodic cycles. All right, and that's it. So the proof of this is sort of apply Fatou Shishikura inequality to the rescaling limits. All right, so one might want to do the same thing for higher degrees. So why not? Let's look at degree 3, or degree greater or equals to 3.
Can I ask you again? So what does it say exactly for Shishikura inequality when you apply to rescaling limit?
So it essentially says that if there is a critical point assigned to any non-repelling periodic cycle. And here, if you have a risk, okay, so if you have by this theorem, if you have a period P cycle whose multiplier is not going to infinity, then you have a rescaling limit, and this rescaling limit consumes already 2 critical points, so you cannot have anything else. Right, so, but in higher degrees, these methods will just fail. I mean, partly because of there is no such nice classification of these rescaling limits for higher degrees. So let me just give you some results along this line. So the first is a result by Sebastian Godillon, which proves that there exists Fn in degree 3 with infinitely many rescaling limits. Right, so it was already known, like you can take, for example, the Macmillan family, which is a sequence of which is a family in degree 4 for degree 4 polynomial for degree 4 rational maps, and these Macmillan families would have infinitely many rescaling limits. And it uses these some kind of a folding methods. And then for degree 3, you can essentially do very similar stuff.
The rescaling limits are what? Polynomial also? Or monomial maps?
Yeah, so they are all monomials. But there's another theorem. I think it's by me, and then also a material 4 and 3 also has some version of that. There exists Fn in graph 3 with infinitely many non-monomial rescaling limits. Right, so I mean, the construction is actually well, let me try to explain like the construction a little bit. I mean, what I'm going to do here is different from the proof in the paper. The paper uses something like a quasi-conformal surgery and to construct these rescaling limits. But if you want one example, then you can actually do something very explicitly. Okay, so here is what I'm going to do. Well, I'm going to give you an example in degree 4, but the construction can also be done in degree 3. So we can start, I mean, the idea is quite simple. We start with this Macmillan family f square, z square plus something like a t square over z square. All right, so I'm switching back to doing something like a family, and then this it's easier to write it in this way. All right, so okay, so what is this dynamics? So you have this Gauss point, and any point can be written as some. I mean, we are particularly interested in this interval, which can be parameterized by t to the some power of alpha times xg. Then you translate this point by some Mobius transformation. So here the Mobius transformation looks like t to the alpha of c. It's in fact an affine transformation. Right, and then an explicit computation shows that when you're restricting to this particular interval, you will obtain a tent map. Right, so you divide this interval into 2, and the map maps the first interval, I1, to I in an orientation preserving way, and it maps the second interval, I2, to I in an orientation reversing manner. And the derivative along these two maps are piecewise linear, and then derivatives are exactly 2. And this has to do with the exponent here, too. Right? Okay, and then this map would have a fixed point. So let me just remark that the periodic cycles, periodic points, of the tent map are in one-to-one correspondence with the rescaling limits. For this family. Right, so, but all of these rescaling families are essentially monomial. And then the trick to get all of these non-monomial is simple. Well, we look at a fixed point, so let R0 be the fixed point. And Rn be the smallest period to the nth point, which is bigger or equals to, which is strictly greater than Rn minus 1. I mean, so you start with R0, and then you look at there will be a period 2 cycle somewhere here. And then you look for the next period 4 cycle, which is bigger than R1. And then you look at the next one. And the family that we are going to look at consists of a sequence of families. So we're going to define sort of a affine map which modifies this map at the scale R to the n. So this is going to be a I from 0 all the way to n of t to the r'th power. Right, so A0 is just going to be a small perturbation on the level of R of 0. And then you follow by an even smaller perturbation and an even smaller perturbation. So just to give you some sense, let's look at A0 composed with F. So what we are going to look, the map then becomes something like a z squared plus t squared over z squared plus some constant that we're going to determine in a moment, A0 times e t to the R0. Right? So when you choose your A0 carefully, and this can be done. For example, if you choose A0 to be minus 1, then this map adds up a little bit of a translation. So the map has a fixed point somewhere here. And for smaller, for those points below this, this fixed point, the map will just rotate governed by this particular A0 here. So you can look at this particular point, this particular family, and then let's call this thing G0. So the tangent map at this point, this particular fixed point, let me denote this by x of 0. X of 0 of G0 is going to be something like 1 minus z squared minus 1, which is non-monomial. And in fact, if you have originally, if you have a period 2 cycle here, this period 2 cycle becomes a period 3 cycle. Right? And then the next step, we can add a small perturbation, and then this small perturbation gives you even more branches. And the original, the originally R2 correspond to a 4 cycle. Now this 4 cycle becomes 3 to the second power, so which is a period 9 cycle here. And so on. So what we're essentially doing is some kind of a renormalization of these maps on the tree. And in the limit, you've obtained a map with more and more non-monomial rescaling limits. And then you take a diagonal sequence, and then you obtain some sequence with infinitely many non-monomial rescaling limits. right? So things can really go bad. Things can be really complicated as long. I mean, this construction also works in degree 3. So things can really go pretty wild when the degree is not 2. In degree 2, you only have 2 rescaling limits. In higher degree, you can get as many as you want. Yes.
But all these rescaling limits should still be PCF, right?
All of the so there.
Can you see the PCF structure?
Yeah. So it depends. Really depends on how you do. One thing you can do is you can make all of these things will have a. In this construction, I think you have a degree 2 critical point of, and then it is. I forgot. I mean, it's not a degree 2, but some critical point mapped to some critical point, mapped to some non-critical point, and then map back to itself. It's always like you have, instead of having a monomial which has a cycle of 2, here like you just increase the cycle to 3. Right. So, I mean. All right, so I mean, the short answer is that a lot of these arguments in degree 2, I forgot to mention in degree 2, and I want to ask a few questions. So the first question is about this. Can we construct a holomorphic family of rational maps with infinitely many non-monomial rescaling limits? I mean, this construction gives a sequence, but I don't know if this sequence can be made into a family. And I should also mention that it's something related to Alex's question. So there are, can we prove that there are only at most 2D minus 2 rescaling limits that are not PCF? So all of these things has to be PCF.
So how do you do it in degree 3? What was it? Is it a weird formula? Or?
Yeah, so I mean, the actual proof is not going to, I mean, this would require a lot of computation and a very precise understanding about this Macmillan map here. Because you want to show that you can always solve the systems. So the argument would give you, is just going to give you, the actual argument is you start with some hyperbolic component, a hyperbolic rational map, and then you do some kind of a quasi-conformal surgery. And then you produce more and more these non-monomial rescaling limit, and then you take the diagonal limit. So you want to construct some hyperbolic rational map with disconnected Julia set, and whose sort of the Fatu components. There are more and more these Fatu components that are finally connected. And then you're going to take the sequence, which is a diagonal argument, and then you get infinitely many. I should probably explain that later. It's yeah. So this argument, I mean, in degree 4, you can have this nice explicit formula, but I don't think this formula actually helps with the understanding of that.
In the monomial case, is that also with a sequence, or is that in a map? So I guess is your question, can you ask the question about, like, just for infinitely many monomial?
Well, yeah, but then this one would just give you infinitely many, right? Monomial. So yeah, so monomial is easy, but I don't know about non-monomial. Okay. All right, so now I want to talk about, well, so yeah, before that, I want to also mention something. we still don't know everything about the boundedness of hyperbolic components in degree 2. So for example, are all hyperbolic components of capture type bounded? So a hyperbolic component of capture type means that you have some periodic attracting cycle, and you have some other critical point which is in the basin of this periodic basin of this attracting cycle, but it's not in the immediate basin, or it's not in the periodic cycle here. So and I don't think we know the answer.
I thought Kiwi had come up with an argument, but maybe never wrote it for another.
That would be interesting. I didn't see any. Yeah, so I think many people have thought about this. Maybe in this room, people may have known the answer of this question. I haven't seen any paper about this. Yeah, but I know like people have thought about this, and then it's an interesting question, even in degree 2.
So, Tony, you have mentioned that for absence theorem, now the most updated result is just for what's the degree? Just degree 2, or do we know anything about that higher degree?
What?
Absence result.
Yeah. So, I mean, you don't expect to. I mean, these questions are hard. I mean, we only know some partial answers to some of the questions. So one of the questions that I want to maybe present in the, I don't know if I have time, but I want to alluding to is this, this conjecture. So maybe I'm going to put it here. So there is a conjecture about these boundedness problems for hyperbolic component. And it was proposed by Kurt McMullen in the 80s that if you have a hyperbolic component of Siampinsky carpet type, is bounded. All right, and then a hyperbolic component of a Siampinsky carpet type simply means that if you pick any map in this hyperbolic component, Julia set is homeomorphic to a Siampinsky carpet. And there are some recent progress, including some of my joint work with Dima Durko of partially resolve this, and then Jeremy Kahn is also having some nice results about this, maybe even prove the whole conjecture. Yes?
Do you know if you can have Java conjugate PCF maps where one hyperbolic component is unbounded and one is bounded?
I have never thought about these questions. What does the Gara orbit of the PCF map, how does it act on the Julia set? I thought, well, the polynomials are all unbounded, but I mean, in general, I don't know. I don't know the answer to that. I think the question was, if you have a PCF map, rational map, and then is it possible to construct a PCF rational map whose hyperbolic component is bounded, but whose Gara conjugate of the hyperbolic component is not? Was that a question? All right. I mean, the thing is that there are only very few hyperbolic components that we know are bounded. All right. Okay, so yeah, so okay, so let's see. How should I see? All right, so since we cannot try to, I mean, I don't think there will be a good way to extending these boundedness results of hyperbolic component in degree 2 in higher degrees. So I want to propose a different approach in order to understand these kind of degenerations. We want to have some geometric control about the orbit of the critical point. So there are two different, as I try to explain at the beginning of this mini course, there are two sources kind of to propose this uniform control on the critical orbit. The first is, so you restrict yourself to certain type of degeneration. And this would help you to understand a lot of boundary points of the hyperbolic component, and it's a very useful tool. I will first talk about this, and maybe towards the end I will just say a few words about some uniform bound that you can obtain by some renormalization theory, a priori bounds of the renormalization theory. All right, so I want to talk about this thing called a quasi-PCF degeneration. So as mentioned in Sabia's talk, these hyperbolic components are essentially modeled by Blaschko product. So I want to first discuss these quasi-PCF degenerations for Blaschko product. So we are going to look at some proper holomorphic maps of degree D on the unit disk. And there are really three possibilities by to classify. There are only three types of these such maps. So by looking at its fixed point. So when you can have a fixed point so the first type, I will call that a hyperbolic. And this corresponds to have a fixed point in the unit disk. And you can also have a parabolic. This would correspond to having a fixed point on the boundary of this disk, and it's parabolic. Or you can have something like boundary hyperbolic. And this corresponds to have a fixed point on the boundary and is attracting. All right, and in a parabolic case, you can have a doubly parabolic or singly parabolic. And then you can sort of distinguish them by looking at the Julia set. Well, if you have a hyperbolic you have a hyperbolic proper degree D map of the unit disk, then the Julia set is just going to be the whole circle. And the dynamics on it is quasi-symmetric conjugate to the standard degree D map, multiplication by D map on the circle. For the doubly parabolic case, the Julia set is again going to be a unit circle here. And in this case, you have two attracting direction and two repelling direction corresponding, giving you which covers like this local picture here. And the singly parabolic looks something like this. So the Julia set now is going to be a Cantor set. And you only have one attracting direction, which also attracts one direction along the circle and one repelling direction along the circle. Okay, so you have some intervals on the circle, and the Cantor set is constructed by taking away all the consecutive preimages of these intervals. And similarly, you have in the boundary hyperbolic case, you have a attracting cycle here. So again, the Julia set is going to be a Cantor set. So we are mainly going to focus on these hyperbolic ones, but these parabolic and boundary hyperbolic, they will appear in the limit as some rescaling limit. All right, so let me first tell you the definition, and then I'll talk about some nice things or some of the things that we can prove using such machinery and why it is useful. So so we are working with the sequence of in BD, and in BD, let me denote this as the space or the moduli space of a hyperbolic Blasch product, hyperbolic proper map of degree D on the unit disk. So we have a sequence of these Blasch product. And we say this Fn is K quasi PCF if the following holds. If we can label all the critical points by C1n all the way to CB minus 1n. So we can label all the critical points, and we have these periodic cycle, this pre-period Li, L1 all the way to LD minus 1, and the period P1 all the way to PD minus 1. Such that if we look at the hyperbolic distance between the Li plus Pi's iterate of the ith critical point to the Li iterate of the ith critical point is bounded by K. Right? So this is some imposed uniform geometric control on the critical point. So let me try to explain this definition a little bit. So these Li's, Pi's, they are constant, does not depend on n. So you look at the Li plus Pi's iterate to Li's iterate of the ith critical point. These 2 points are uniformly bounded along the sequence. So you should think about these critical points as some kind of pseudo orbit with the pre-period Pli and period Pi. And the distance is quantified by this capital K, which controls the arrow of the hyperbolic distance. All right, so a lot of many examples that people have already studied in the past would give these quasi-PCF degeneration. So let me just remark, there are these pinching deformation studied by Peter Hansiski, Lei, Shui, and many other people. These the spinning deformation by Kevin and Lei. They all provide examples of these quasi-PCF degeneration. But this, I believe this turns out this is going to be more general than these spinning or these pinching deformations. So the schematic picture looks like the following. So, or maybe I'll give you one example, or some examples of such degeneration. And then I will say what we can use for such, what kind of example, what kind of theorems we can prove using these examples, which also related to the decomposition of these rational maps, as I mentioned in the very earlier, in the first lecture. And then I will say maybe a few words, some of the generalizations to such degenerations. All right, so okay, so I'm going to write down the formula for a very explicit example, but the actual formula is not really important. So I'm going to draw some pictures here. So one can consider let's say a degree 2 biological product which is of the form. This particular form where Rn goes to 1. So its dynamics looks like the following. So the origin is going to be fixed, and then you have one critical point which goes to I suppose it's minus Rn e to the I p over q. P and q are fixed, yes. So you fix a particular rotation number, and then you let this Rn to go to 1 radially, and then this would provide one example. So the picture looks something like the following. So there is a critical point, and then the critical point starts to rotate. I don't know. It has to have some well-defined rotation number, but under qth iterate, this particular point is Cn, and this particular point is supposed to be the qth iterate of Cn. The hyperbolic distance between Cn and the qth iterate of Cn remains uniformly bounded along the sequence. Right? I should say that this critical point is escaping to infinity, so the distance between 0 and then the critical point is going to infinity. So it's a degenerating sequence, but somehow the qth iterate of the critical point is remain bounded uniformly with respect to Cn. And such.
Yes. So when you say degenerating, here you mean in your space BD modulo conjugacy or whatever, but or no, but not that inside MD are also degenerating.
Yeah. So well.
Just in BD.
But you can do Shor's reflection, and then you obtain a rational map. These biological products are also rational map, and if it degenerates as proper map of degree 2, except for some situations you have, I mean, it's also degenerating in the moduli space of rational maps.
So not all of them are.
So there is some. It depends on the particular parameterization that you're using. If you parameterize your biological product in this particular way, there is only one sequence. If the multiplier goes to 1, then there is a possibility that the sequence is non-degenerating. Yes.
Right. Okay, but for you, degenerating now means
In
in BD.
BD, yes.
Is this a model for what happened in the main cardioid as well?
Yes, I mean, in this particular example, this exactly corresponds to the radial convergence along the P over Q, the main cardioid of the towards this parabolic point with rotation number P over Q. Yes. Right. So this can be constructed by some pinching deformation, and this was one particular example. Yeah, so maybe let me just say a few words on what kind of things we can prove using these methods. Right, so first that we can actually get a nice, okay, so some applications of these. Right, so let me try to draw the parallel of the what we all know very well, which is the sort of the main cardioid. So this is particularly the hyperbolic component that we're interested in here. You have the main cardioid, which is the hyperbolic component containing z squared in the space of polynomials. What we know about this particular main cardioid is we know these parabolic or these geometric polynomials on the boundary. So the geometrically finite maps on the boundary of H2 are in one-to-one correspondence with this rotation number P over Q. Right? And then these are exactly those points where you see bifurcation to another hyperbolic component. Right? So you have this nice description about these geometrically finite maps on the boundary of H2. Another sort of interesting observation here is that the boundary of H2 is topologically a circle. It has a cusp point, this cauliflower parameter, but it is a topological circle. Right? So using these quasi-PCF degenerations, we can actually also derive a similar statement for higher degree analog of such hyperbolic components. So let me just write it as very vaguely. There is a more precise statement you can find in the papers, but let me just kind of like in the remaining 10 minutes, I'm just going to be really like loose and then just talk about some applications, and I think these type of things is worth looking to explain why these kind of degeneration is worth looking at to study more. So, for example, so we can look at HD in the space of polynomials degree D, and these are hyperbolic components of degree D, which is the hyperbolic component that contains z to the d. And we're only restricting to the moduli space of polynomials. So what we can use these quasi-PCF degenerations to understand these geometrically finite polynomials on the boundary of HD, or I should say at least combinatorially. One thing that we don't know is these the boundary of the hyperbolic component may not be close on the quasi-conformal deformation. And it's an extremely hard question. I believe it's an extremely hard problem to understand what actually, what is the actual boundary of these hyperbolic components. But at least combinatorially, we can describe exactly what are those geometrically finite maps on the boundary.
So did you define for us geometrically finite?
I haven't. I was planning to just do it loosely. So geometrically finite means it's every critical point on the Julia set has finite orbit. Yep. So you don't have any infinite critical point, critical orbit on the Julia set. So it can have parabolic periodic points, It can, but it cannot have a zero point, and it cannot have like in polynomial, it will never have a Hermann rings anyway. Right? And we can also sort of like using this to understand the second type of analog of such question. And we can use that to construct self-bumps on the boundary of HD, where D is at least 4. So what a self-bump means is the picture locally looks something like this. So you have some polynomial on the boundary of HD such that for any small neighborhood, U, which contains P, the intersection of U with HD is disconnected. So locally, you can see using some one-dimensional slice, the boundary of the main hyperbolic component of degree 4 has this self-bumping structure. There is actually some picture produced in this way. Right? And then these are sort of like applications when we don't have degeneration, when we study the deformation spaces of polynomials. And if we do have degeneration, if we want to understand these boundedness problems, we can apply all these machineries that we discussed previously to such specific degeneration. And unfortunately, we will not be able to discuss any sort of like proof ideas for such things, but we can show something like if H is Sierpinski carpet, and Fn in this Sierpinski carpet hyperbolic component is quasi-PCF, then Fn is bounded. Right, so some kind of a statement like this. Right, so I should say that here the definition of quasi-PCF is for Black-Scholes product, but as Sabia mentioned in his talk, these hyperbolic components are modeled by this Black-Scholes product. So we say that it is quasi-PCF if under this model, this degeneration is quasi-PCF. Right, so potentially all of these geometrically finite ones can be obtained using some iterations of these quasi-PCF degeneration. So we expect, and we also conjecture, there is a conjecture that says that these geometrically finite ones should be dense. So potentially we cover a lot of these maps on the boundary that are bounded. And to go beyond these geometrically finite ones, we cannot use this imposed condition about the degeneration. And somehow we can, I mean, this is, let me put it as a theorem, which is a joint work with Dimadurko. And the preprint is available on the website. We still need to fix some precise references to this a priori bound. That should be ready soon. I mean, that's what I said maybe half a year ago, but it should be ready soon. Where we sort of use some kind of like Ziegel a priori bounds to promote this, to study this conjecture in for certain type of hyperbolic component, which is hyperbolic component of disjoint Sierpinski carpet. Type is bounded. Right, so here, disjoint means that we have the maximal number of attracting cycles again. So we have exactly 2D minus 2 attracting cycles. And the Sierpinski carpet means that if you take any map, the Julia set is homeomorphically to a Sierpinski carpet. And in fact, our method works in general, and we can study the boundary at infinity of any disjoint type hyperbolic component. And then we believe we actually do have an algorithm, both a positive algorithm and a negative algorithm, to determine when a when a certain degeneration is bounded and when a certain degeneration is unbounded. I mean, in this case, the hyperbolic component is homeomorphic to its multipliers of the 2D minus 2 periodic cycles. So the boundary points consist of all those. You can use this closure of 2D minus 2 minus D, the polydisk, to model the boundary points of these hyperbolic components. And then we believe we do have an algorithm of detecting when these boundary points are bounded and when these points are unbounded, except for some situations where you have multiple parabolic points. All right, so I'm going to stop here, and thank you for